Welcome to today's problem walkthrough. We'll be tackling LeetCode problem number 748, titled Shortest Completing Word. This problem challenges us to find the shortest word that satisfies specific conditions. Let's dive in to explore the problem and its potential solutions. In this problem, you are given a string called license plate and an array of words called words. Your goal is to find the shortest completing word from the array. A completing word is defined as a word that contains all the letters present in license plate, while ignoring case and non-alphabet characters. Importantly, each letter in license plate must appear in the word at least as many times as it appears in license plate. Once you identify the completing word, you return the shortest one. If multiple words qualify and have the same length, you choose the word that appears first in the array. The inputs to the problem include license plate, which has a length between 1 and 7, and an array words where the number of words can be as large as 10,000, and each word can have up to 15 characters. The output is a single string representing the shortest completing word that satisfies these conditions. Let's take a look at the first example. Here, the license plate is given as 1s3pst, and the array of words is step, steps, stripe, stepple. First, we extract the letters from license plate, ignoring all non-alphabet characters and case. This gives us the letters S, P, and T. Now, we check each word in words to find a word that contains all these letters with at least the required frequency. Both step and steps satisfy the condition, but steps is the shortest completing word. Therefore, the output is steps. Now, consider the second example. Here, the license plate is 1s3 and the array of words is looks, pest, stew, show. Extracting letters from license plate gives us just the letter S. Among the words in the array, pest is the shortest word that contains the letter S. None of the other words are shorter and still meet the requirements. Therefore, the output in this case is pest. In the third example, the license plate is at $12, and the array of words is hello, habit, hat, apple. From license plate, we extract the letters A and H. Among the given words, hat is the shortest word that contains both A and H. The other words either don't contain all the required letters or are longer than hat. As a result, the output for this example is hat. Finally, remember that we must always ignore non-alphabet characters and treat the comparison as case-insensitive. The constraints also ensure that a valid completing word will always exist in the input array. To solve the shortest completing word problem, one approach we can consider is the brute force method. The idea here is to check each word in the given array of words to determine if it meets the criteria of a completing word for the license plate. First, we extract all the alphabetic characters from the license plate, convert them to lowercase, and count how frequently each character appears. Once we have this character frequency map, we iterate through each word in the array and check if it contains all the required characters in at least the same frequency. If multiple words satisfy this condition, we return the shortest one. While this method is straightforward and easy to understand, it isn't very efficient. For every word in the array, we perform a frequency comparison, which can become computationally expensive, particularly if the license plate has many unique characters or the words array is very large. The time complexity here is n*m, where n is the number of words and m is the average length of each word. To improve on the brute force approach, we can implement an optimized method that uses character frequency matching more efficiently. Instead of recomputing the frequency of characters in the license plate for every word, we can pre-process this information once at the start. Specifically, we extract the alphabetic characters from the license plate, convert them to lowercase, and compute their frequency using a dictionary or array. Then, as we iterate through each word in the list, we calculate its character frequency and compare it to the pre-computed frequency of the license plate. If the word satisfies the condition, we check if it's shorter than the current shortest completing word and update our result accordingly. This method avoids redundant computations, as the license plate's character frequencies are calculated only once. Another alternative to consider is sorting the words by length before checking for completing words. This way, we can terminate early once we find the first valid word. However, sorting introduces additional overhead, which can be avoided by dynamically tracking the shortest word during the iteration. Overall, the optimized approach has a time complexity of n*m, but it minimizes unnecessary operations and is more efficient than brute force. The optimized approach is the most effective strategy for this problem because it balances clarity and performance. Pre-computing the character frequencies for the license plate simplifies the comparison process and eliminates redundant calculations. By iterating through the words array directly and dynamically tracking the shortest completing word, we avoid the need to sort the array, which could add unnecessary overhead. One key insight here is that the character frequency of the license plate remains fixed throughout the process, so pre-computing it allows us to reuse this information efficiently. Additionally, ignoring non-alphabet characters and treating the input as case-insensitive further simplifies the implementation. While the brute force method is easier to conceptualize, it becomes inefficient for larger inputs. Similarly, sorting-based methods may allow for early termination but come with their own computational cost. The optimized approach avoids these trade-offs, making it both practical and robust for real-world scenarios with varying input sizes. The goal of this problem is to find the shortest word from a given list that can be considered a completing word for a license plate. A completing word is one that contains all the letters from the license plate, respecting their frequencies, and case does not matter. The first step in solving this is to focus only on the alphabetic characters in the license plate. Any numbers or special characters are ignored, and all letters are converted to lowercase to ensure case insensitivity. For example, if the license plate is ABC123 at #D, we extract only the letters A, B, C, D. This simplification is important because it allows us to work only with the relevant data for the problem and ignore any extraneous information. After extracting the alphabetic characters, the next step is to count the frequency of each letter in the license plate. This is essential because the completing word must match these frequencies, ensuring that even repeated letters are accounted for. Using a tool like Collections Counter makes this process efficient by automatically creating a frequency map. For example, if our extracted letters are A, B, C, D, the resulting frequency map is A1, B1, C1, D1. Once we have this map, we can proceed to check each word in the given list to see if it satisfies the condition of containing at least as many of each required letter. For every word, we count its letter frequencies and compare them to the license plate's frequency map. For instance, if the license plate requires A1, B1, and the current word is Baba, its frequency map, B2, A2, shows that it meets the requirements, making it a valid completing word. The next step is to efficiently identify the shortest valid completing word. As we iterate through the list of words, we keep track of the shortest valid word we encounter. Each time a new valid word is found, we update our stored result if the new word is shorter than the current shortest. This way, we avoid unnecessary sorting or extra passes through the data. To illustrate, if the valid words found so far are Baba, ABC, and we encounter AB, we update the shortest word to AB because it is the smallest. Some key insights here include normalizing all letters to lowercase for case insensitivity and ensuring that repeated letters in the license plate are handled correctly by matching their frequencies. This approach ensures that we not only find a valid completing word but also the shortest one, as required by the problem. To implement this solution effectively, we rely on specific data structures. A counter or dictionary is used to store letter frequencies for both the license plate and each word. These structures allow for constant time lookups and make frequency comparisons efficient. The final result, which is the shortest valid word, is stored as a string. In terms of complexity, extracting letters and counting their frequencies from the license plate takes L, where L is the length of the string. Processing each word involves counting its letter frequencies, which takes W, for a word of length W, and comparing frequency maps, which is O1, since the number of letters in the alphabet is constant. If there are n words in the list and the average word length is W, the overall time complexity becomes L plus n asterisk W. This ensures that the solution is efficient, even for larger inputs. When solving this problem, it's critical to handle edge cases effectively. For instance, if the license plate contains no alphabetic characters, all words are automatically valid, and the shortest word in the list should be returned. If no word satisfies the conditions, an empty string should be returned, or the behavior should align with the problem's constraints. If multiple words are equally short and valid, the first one encountered in the input list is returned, assuming the order matters. Finally, the solution must seamlessly handle mixed-case letters, digits, and special characters in the license plate, ensuring that these are processed correctly without affecting the result. For example, given the input license plate equals 1s3pst and words equals step, steps, stripe, stepple, we would expect to find the shortest completing word that meets these constraints. To execute the solution, we start by extracting the alphabetic characters from the license plate, resulting in S, P, S, T. Next, we count their frequencies, producing S2, P1, T1, then, we check each word against this frequency map. The word step has a frequency map of S1, T1, E1, P1, which is invalid because it lacks the second S. The word steps has a frequency map of S2, T1, E1, P1, which meets the requirements and is valid. The word stripe has a frequency map of S1, T1, R1, I1, P1, E1, which is invalid because it also lacks the second S. Finally, stepple has a frequency map of S1, T1, E1, P2, L1, which is also invalid for the same reason. The shortest valid word is steps, which is returned as the result. The given code solves LeetCode problem 748, shortest completing word. The goal is to find the shortest word from a list that contains all the letters, case insensitive, from the license plate, including their frequencies. First, the counter class from the collections module is imported to handle frequency counting efficiently. Inside the shortest completing word method, the code extracts all alphabetic characters from the license plate string, converts them to lowercase, and counts their frequencies using counter. This ensures that we focus only on letters and ignore numbers or special characters. Next, the method initializes two variables, shortest underscore word to store the current shortest valid word, and shortest underscore length, set to infinity, to keep track of the shortest length. The method iterates over each word in the words list. For each word, a frequency counter, word underscore counter, is generated. It then checks if the word contains at least the required number of each letter specified in the license underscore counter. This is done using a condition that verifies if every letter's count in word underscore counter is greater than or equal to its count in license underscore counter. If a word meets the requirements and its length is smaller than the current shortest underscore length, the method updates shortest underscore word and shortest underscore length with the current word and its length, respectively. Finally, after evaluating all words, the method returns the shortest underscore word, which is the shortest completing word. This implementation is efficient and concise, handling edge cases like mixed case letters, non-alphabetic characters in the license plate, and multiple valid words in the list. The use of counter ensures that frequency comparisons are straightforward and clean. Here, we start by creating a method called shortest completing word. The goal of this method is to determine the shortest word from a given array that contains all the characters from the license plate, irrespective of case or non-alphabetic characters. First, we initialize an integer array license count of size 26 to track the frequency of alphabetic characters in the license plate. Using a for each loop, we iterate over each character in the license plate. If the character is a letter, we convert it to lowercase and calculate its position in the alphabet using character.toLowercase ch. We then increment the corresponding index in the license count array. After calculating the frequency of characters in the license plate, we define two variables, shortest word to store the result and shortest length to keep track of the length of the shortest matching word. Next, we iterate over the list of words. For each word, we check if it qualifies as a completing word by calling the helper method isCompletingWord. If the word meets the condition and its length is shorter than the current shortest length, we update shortest word and shortest length. Finally, the method returns the shortest completing word once the loop finishes. The helper method isCompletingWord is responsible for determining whether a given word satisfies the character frequency requirements of the license plate. Inside this method, we first create an integer array word count of size 26 to track the character frequencies in the current word. Using a for each loop, we iterate over each character in the word, calculate its position in the alphabet using ch, and increment the corresponding index in word count. After populating the frequency array for the word, we compare it against license count. We loop through all 26 indices, and for each index, we check if the frequency in word count is less than the corresponding frequency in license count. If any required character is missing or insufficient in the word, we return false immediately. Otherwise, if all character requirements are met, we return true. This helper method ensures that the main function can efficiently verify if a word is a completing word, enabling the overall solution to work seamlessly. To solve the problem, we start by processing the license plate string. First, we extract only the alphabetic characters and convert them to lowercase. For the input 1s3pst, this results in the characters s, p, s, and t. Next, we compute the frequency count of these characters using Python's counter class, giving us license_counter equals counter, s2, p1, t1. This tells us that we need 2 s characters, 1 p, and 1 t in any completing word. After this, we initialize 2 variables, shortest_word, which starts as none, and shortest_length, which is set to infinity. These will help us keep track of the shortest completing word and its length as we process the list of words. Now, we process each word in the words array to check if it can complete the license plate requirements. First, we analyze the word step. Its frequency count, word_counter, is counter, s1, t1, e1, p1. Comparing this to license_counter, we see that step has only 1 s, but we need 2. Therefore, this word is skipped. Next, we look at steps. Its frequency count is counter, s2, t1, e1, p1. This satisfies all the requirements of license_counter, it has 2 s, 1 p, and 1 t. So, we update our shortest variables, shortest_word becomes steps, and shortest_length is set to 5. Moving on, the word stripe has a frequency count of counter, s1, t1, r1, i1, p1, e1. Since it only has 1 s, it doesn't meet the requirements, and we skip it. Finally, for the word steple, its frequency count is counter, s1, t1, e2, p2, l1. Checking steple, we find that it only has 1 s but requires at least 2. Therefore, it does not satisfy the license_counter and is skipped. At the end of this process, the shortest completing word for the license plate 1s3pst is steps. We return this as the result. Now, let's look at another example. For license plate equals 1s3 456 and words equals, looks, stu, show, we follow the same steps. First, we process the license plate. Extracting the alphabetic characters and converting them to lowercase gives us just s. The frequency count is license_counter equals counter, s1. With the license_counter ready, we initialize the variables shortest_word as none and shortest_length as infinity. Then, we begin processing each word in the words array. For the word looks, its frequency count is word_counter equals counter, o2, l1, k1, s1. Since it has at least 1 s, it satisfies the license_counter. We update the shortest variables, shortest_word becomes looks, and shortest_length is set to 5. Next, we analyze stu. Its frequency count is counter, s1, t1, e1, w1. This also satisfies the license_counter and, with a length of 4, it's shorter than looks. Therefore, we update shortest_word to stu and shortest_length to 4. Finally, we examine show. The word show has a frequency count of counter, s1, h1, o1, w1. It satisfies the license_counter because it contains 1 s. However, since its length is 4, it isn't shorter than the current shortest word, stu. As a result, we skip updating the shortest variables. At the end of this process, the shortest completing word for the license plate 1s3 456 is stu, which we return as the result. Now, let's consider another example. For license plate equals ABC 123 and words equals ABC, CBA, cab, we start by processing the license plate. Extracting the alphabetic characters and converting them to lowercase gives us a B and C. The frequency count is license_counter equals counter, of 1, B1, C1. With the license_counter prepared, we initialize shortest_word as none and shortest_length as infinity. Then we process each word in the words array. For the word ABC, its frequency count is counter, of 1, B1, C1. This satisfies the license underscore counter because it contains one of each required character, A, B, and C. With a length of 3, we update shortest underscore word to ABC and shortest underscore length to 3. Next, we check the word CBA, which has a frequency count of counter, C1, B1, 1. It also satisfies the license underscore counter, but since its length is 3, it isn't shorter than ABC. So, we skip updating the shortest variables. Finally, we evaluate cab. The word cab has a frequency count of counter, C1, 1, B1. It satisfies the license underscore counter as it contains 1 A, 1 B, and 1 C. However, with a length of 3, it is not shorter than the current shortest word, ABC. Therefore, we don't update the shortest variables. At the end of this process, the shortest completing word for the license plate ABC 123 is ABC, which we return as the result. This concludes our step-by-step solution walkthrough for this problem. Here, we are analyzing the time complexity of the solution step by step. First, processing the license plate to build the license underscore counter involves iterating through the string and extracting alphabetic characters, which takes L time if the length of license plate is L. Converting these characters to lowercase and building a counter for their frequencies is also L, since, in the worst case, all characters are alphabetic. Next, we examine the words list. If there are n words and the average length of a word is m, processing each word involves creating a counter for character frequencies, which takes m. Additionally, the all function checks if the word satisfies the conditions in license underscore counter. This involves iterating over at most 26 key-value pairs, since there are only 26 alphabetic characters, making this an O1 operation. Multiplying by the n words, this step has a time complexity of n*m. Now, for updating the shortest word, we compare the length of each word that meets the conditions to the current shortest word. This operation is O1 per word. Combining the steps, the total time complexity becomes OL for processing license plate and n*m for iterating through the words, resulting in an overall time complexity of OL plus n*m. Next, we analyze the space complexity. The license underscore counter stores the frequency of characters in license plate. Since the maximum number of distinct characters is 26 for the English alphabet, the space required is constant, or O1. Additionally, the space complexity includes the word underscore counter created for each word in the words list. This requires m space, where m is the length of the word. Since the word underscore counter is reused for each word, it does not add up across words. This means the space complexity for this part is m. Other variables, such as shortest underscore word and shortest underscore length, use constant space, or O1. Combining these factors, the total space complexity is O1 for license underscore counter plus m for word underscore counter, resulting in m overall, where m is the maximum length of a word in the words list. To gain further insight, let's look at the best, average, and worst cases. In the best case, the first word in the list satisfies the conditions, and minimal further comparisons are necessary. While the time complexity remains OL plus n*m, the constants are smaller. For the average case, we expect to check most words in the list, so the time complexity stays OL plus n*m. In the worst case, all words must be checked, and the license underscore counter contains many characters, leading to the same time complexity but with larger constants due to more comparisons. By comparing this solution to a brute force approach, which involves repeated substring checks for each character in license plate, we see a significant improvement. The naive approach has a time complexity of n*m*k, where k is the number of characters in license plate. In contrast, the optimized solution reduces this to OL plus n*m by leveraging counter objects and the all function. Finally, the big O analysis can be mathematically verified. Processing license plate involves linear operations in L, giving OL. For each word in words, the operations depend linearly on the word's length m, resulting in n*m. When combined, the total time complexity is OL plus n*m, which is much more efficient than the naive approach of n*m*k. Regarding space complexity, the dominant factor is the counter created for a single word, which requires m space. This confirms that the total space complexity is O(m), making the solution both time-efficient and space-efficient for the given problem. When solving this problem, there are a few common mistakes to watch out for. First, many people forget to normalize the license plate. This means they might overlook removing non-alphabetic characters like numbers or special symbols, or they fail to convert all the letters to lowercase. This can cause mismatches when comparing the license plate to the words in the list, especially because license plates often contain mixed cases and non-alphabetic characters. Next, inefficient frequency comparisons are another common pitfall. If you repeatedly recompute the frequency of letters for the license plate or each word, it unnecessarily increases the time complexity. Instead, pre-computing these frequencies once and reusing them is much more efficient. Lastly, ignoring edge cases is a big problem. Scenarios like having an empty license plate, all words being invalid, or multiple words tying in length need to be accounted for, as missing these can lead to runtime errors or incorrect outputs. For example, if no word matches, returning an empty string incorrectly might cause issues depending on the problem's requirements. Now, another mistake to avoid is not filtering shorter words early. If a word is shorter than the number of unique letters in the license plate, it's impossible for that word to meet the requirements, so there's no point in checking it further. Skipping this filter wastes valuable time on unnecessary comparisons. Another issue arises from the incorrect handling of duplicate letters. For example, if the license plate requires 2 occurrences of a letter, some might incorrectly assume that just 1 occurrence in a word is sufficient. This is not the case. Words need to have at least as many occurrences of each required letter as the license plate specifies. Overlooking this can lead to selecting invalid words that don't truly complete the license plate. In interviews, this problem typically tests several key skills. First, it's important to recognize the underlying pattern of working with frequency counts and filtering. A frequency map, or dictionary, is ideal for storing the occurrences of each letter in the license plate. Optimization is another focus area. While brute force might work for an initial approach, you should be prepared to improve efficiency by pre-computing frequencies and filtering unnecessary comparisons. Demonstrating edge case awareness is also critical. Bring up scenarios like no valid words being present or ties in word length, and discuss how you would handle them. This shows your thoroughness to the interviewer. Finally, communication is key. Be sure to explain your thought process, including trade-offs between clarity and efficiency. For example, talk about whether pre-computing frequencies is worth the extra memory it uses. If you want to practice related problems, consider problems like valid anagram or ransom note, which also deal with letter frequency comparisons, or group anagrams and sort characters by frequency, which involves sorting or frequency counting in different contexts. There are also alternative approaches you can consider, each with its own pros and cons. A brute force approach with inline checks compares the required letters directly with each word. While simple to implement, it's inefficient, with a time complexity of O(n*(m), where n is the number of words and m is the average word length. A better option is to pre-compute the license plate frequencies and compare them against pre-computed word frequency maps. This is faster, with a complexity of O(n*(k), where k is the alphabet size, but it does require additional memory for the frequency maps. Filtering short words early is another effective strategy. By eliminating words that are too short to meet the requirements, you reduce the number of comparisons you need to make. The trade-off here is implementing logic to determine the minimum length threshold. Finally, sorting the words by length is a clever way to process shorter words first and find the answer quickly. Once you find the first valid word, you can return it immediately. However, sorting can add extra memory overhead, so that's something to consider when evaluating this approach. Great job! Today, we explored the shortest completing word problem, discussed its challenges, and reviewed a brute force approach. Remember to focus on efficiency and optimization as you refine your solutions. Thanks for joining, and see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!